We have thought that the laws of the universe are precise, rational, and predictable since the beginning of modern science. But what if I told you that the universe shouldn't exist based on our calculations? Indeed, something went horribly wrong, or maybe right, at the beginning of the universe, in accordance with the established laws of physics. Perhaps nature has made a huge error that keeps us here, breathing and looking at the sky, an error that contradicts our conception of life itself. The problem starts with symmetry, a basic tenet of physics. The Big Bang equations predict that matter and antimatter should have been produced in precisely equal quantities. The issue? Pure energy is released when matter and antimatter collide and are totally destroyed. This implies that everything should have been destroyed at the time of the universe's creation if it were completely symmetrical. However, something occurred that threw that equilibrium off. The second after the Big Bang did not see the end of the universe. Instead, here we are, with planets turning, life emerging, and stars flashing. Why there is more matter than antimatter is the grand question that has baffled scientists for decades. How did the cosmos manage to endure when its perfect symmetry was broken? This goes beyond simple scientific interest. Finding the solution to this mystery has the potential to completely reinterpret our knowledge of physics and even uncover previously unknown fundamental forces of nature. After all, if symmetry was broken, it indicates that there is still something about the universe's operations that we do not fully understand. What might it be? To uncover this solution, scientists from all around the world have devoted their efforts. They look into processes that could have led to this cosmic aberration, examine subatomic particles, and model the universe's creation in sophisticated labs. But all we have so far are fascinating hints and deepening questions. What if our understanding of the universe's laws is wholly incorrect? Is it possible that our understanding of physics is but one piece of a much bigger picture? The very fact that we are here could be a sign that we are still missing something essential. Furthermore, this problem has its roots in the Big Bang, the universe's initial beginning, as we shall discover later. Consider a scenario in which the cosmos was condensed into a point no bigger than an atom. Time, space, and everything we know were created when the singularity exploded with unfathomable fury some 13.8 billion years ago. At least that's what we think. Everything started with that great event, the Big Bang. However, there is a troubling detail. That explosion should have produced equal amounts of matter and antimatter in accordance with the principles of physics. The issue? The cosmos would have immediately destroyed itself if that had occurred. However, for some reason, that didn't happen. Our best hypotheses suggest that there were 1,000,000,001 particles of matter for every billion particles of antimatter generated in the Big Bang. Although it might not seem like much, the cosmos was able to live because of that slight imbalance. No planet would have developed, no star would have flared, and we would never have come to worry about it if it weren't for that tiny loophole in the cosmic code. One of the biggest puzzles of contemporary science is this cosmic asymmetry. What made that tiny but significant difference? Was it some unidentified physics process? A particle that we haven't found yet? Or is it because the universe's laws are not as unchangeable as we formerly believed? Scientists are motivated to look into the most fundamental forces of nature and the deepest characteristics of matter in order to find this solution. Particle accelerators such as the Large Hadron Collider, LHC, have been simulating conditions similar to the Big Bang for decades in an attempt to see how that imbalance developed. However, the findings are still unclear. We have found previously undiscovered exotic particles and events, yet the big question remains unanswered. Our current theories may be lacking if we are unable to comprehend the reason for the symmetry violation. It's possible that the standard model of particle physics is merely a rough outline of a more comprehensive and profound theory that we haven't yet discovered. And what if that new theory could not only explain why we are here, but also uncover new particles and forces that could completely change the way we perceive the world? The universe still defies us in actuality. The nature of science is that every new finding raises new questions. One thing, however, is certain. The Big Bang was not just a chance explosion. Rather, it marked the start of a riddle that we are now attempting to unravel. The conflict between matter and antimatter, if there is one, is what determines the universe's history. With the exception of one essential feature, their opposing electric charges, these two objects are identical, much like mirror images. There is an antiproton for each proton. There is a positron for each electron. What happens when these particles collide? According to Einstein's well-known equation, E equals mc squared, the outcome is complete annihilation, which turns all of their mass into pure energy. According to science, matter and antimatter were created in precisely equal numbers at the time of the Big Bang. If that had been the case, the antimatter counterpart would have immediately destroyed every atom of matter. The universe wouldn't have existed for more than a second. Nevertheless, something startlingly disrupted that flawless symmetry. Somehow there was a little surplus of matter over antimatter. Even if it didn't seem like much, that difference was sufficient to keep the cosmos alive. But why that imbalance happened is still a big mystery. A preference for matter over antimatter is not anticipated by the fundamental rules of physics. Based on what we currently know, they ought to have been produced in the same quantities. However, the fact that we are here at all indicates that this did not occur. Scientists have used incredibly complex experiments to investigate this mystery. Restoring the conditions of the primordial cosmos and observing the interactions between matter and antimatter at subatomic scales are two goals of the Large Hadron Collider, LHC, the largest particle accelerator in the world. Physicists are looking for a fundamental asymmetry that would explain why matter remained while antimatter essentially disappeared. But what if that asymmetry wasn't only a cosmic oddity? What if matter existed under the influence of an unidentified force, a secret principle? According to some scientists, that primordial imbalance might have been caused by particles that haven't been found yet. This would imply that our current understanding of the rules of physics is lacking, and that a more complete model may be on the horizon. Everything we know has been molded by the conflict between matter and antimatter. There wouldn't be any planets, stars, or life on Earth today if the cosmos had followed the route of perfect symmetry. The fact that we are here at all is a sign that something fundamental is happening in the universe. Are we, however, on the verge of discovering that answer? We are forced to consider the fundamentals of physics while we look for the cause of that imbalance. And if we continue down that route, we come into a key figure in this narrative: Andrei Sakharov, the man who postulated the circumstances in which such imbalance would transpire. How can we explain the universe's seeming ability to outsmart itself if science is founded on unchangeable and predictable laws? The issue of symmetry is more than just a theoretical one. It poses a danger to the foundation of our understanding of reality. Something doesn't add up if the calculations indicate that matter and antimatter ought to have totally destroyed one another. And it indicates that there are pieces missing from this cosmic puzzle when the equations are unable to account for what we see. One of the biggest problems in contemporary physics is this conundrum. Scientists have been searching for other theories for decades, but none have proved entirely satisfactory. Are our hypotheses incorrect? Or is there anything about nature we still don't fully comprehend? The Soviet physicist Andrei Sakharov put forth a potential remedy in the 1960s. According to his theory, 3 essential requirements had to be satisfied for the universe to favor matter over antimatter. These requirements, which came to be known as the Sakharov criteria, served as the foundation for the investigation into this mystery. There must be a mechanism that produces more baryons, matter particles, than antibaryons, antimatter particles, which is known as the violation of baryogenesis. The second is that the C and CP symmetry is broken, indicating that matter and antimatter are not treated exactly alike in the universe. The third need is that this imbalance had to have arisen in a chaotic setting, such as the Big Bang, or out of thermal equilibrium. Nobody has been able to fully demonstrate these conditions in a lab setting as of yet. Nonetheless, there is evidence that mesons, which may decay slightly differently depending on their composition, experience minor symmetry violations. These minor variations might hold the secret to what transpired at the dawn of the universe. If Sakharov's theory is right, this would suggest that there are phenomena out there that we haven't yet noticed. Could such imbalance have been caused in part by hidden particles? Or did unidentified forces shape what we see today at the beginning of the universe? Or are we about to make a discovery that would completely change how we think about the universe? One thing is clear, though. The symmetry problem will persist in challenging our understanding of the cosmos as long as we are unable to come up with a conclusive solution. And we examine the remarkable findings that scientists have discovered in recent decades as we go forward in our quest for that truth. There is a profoundly disturbing aspect of our existence when we examine the basic equations of physics. According to theory, the Big Bang produced equal amounts of matter and antimatter. Yet this should have resulted in the universe's total destruction. All matter particles ought to have discovered their antimatter counterparts and combined to become pure energy. However, an extraordinary event occurred. A tiny imbalance existed, a piece of stuff that had not been completely destroyed. Everything we know today, including galaxies, stars, planets, and even us, was formed by that tiny excess, so tiny that it almost seems inconsequential. The topic of why the cosmos broke its own symmetry, however, is unsettling. Symmetry is one of the most basic laws of existence, and physics teaches us that the universe follows exacting patterns. There should have been a balanced cosmos with just light if matter and antimatter had been generated in the same manner. However, that obviously did not occur. What preferred matter over antimatter is the question at hand. The secret to comprehending the underlying laws of the cosmos may lie in the interference that occurred during the early cosmic process. Scientists are investigating the possibility that certain subatomic particles do not precisely adhere to the laws of symmetry. K and B meson experiments have demonstrated that the decay of these particles tends to create more matter than antimatter. The initial imbalance may have been caused by this symmetry breaking, which is referred to as CP, charge parity violation. Even though the explanation is fascinating, it is still insufficient to explain the stark difference between the current universe's abundance of matter and its almost complete lack of antimatter. According to a different theory, that imbalance may have been fundamentally caused by the very nature of time. According to some ideas, there may be a preferred direction for cosmic events, meaning that the laws of physics are not entirely time reversible. If that were accurate, it would imply that matter and antimatter may have evolved in somewhat different ways from the beginning of the universe, ultimately leading to an accumulation of matter. The fact that we are here is a cosmic anomaly, regardless of the explanation. Our existence contradicts the most fundamental physics predictions, indicating that there is something deep and mysterious about the universe's laws that we do not yet fully comprehend. And while, though researchers are still working to solve this puzzle, certain new findings may offer vital hints as to what actually transpired in the early universe. Humanity has been attempting to comprehend why the cosmos did not self-destruct at the time of its birth for decades. Reality contradicts theory, which states that it should have destroyed itself. The issue is that this disparity cannot be explained by the laws of physics. Recent findings, however, have the potential to upend our understanding of this mystery and spark one of the biggest scientific revolutions in history. Experiments at the Large Hadron Collider, LHC, the biggest particle accelerator in the world, produced one of the most fascinating hints. Researchers started examining the behavior of B mesons, which are unstable particles that only exist for a very short time before fading. They made the astounding discovery that these particles do not decay like their antimatter cousins. This implies that even at subatomic sizes, the universe may have a tiny bias for matter. Even more significant, though, is the possibility that this slight variation was precisely what made matter survive the Big Bang. The enigmatic function of neutrinos is another element that has attracted the interest of physicists. These nearly spectral particles move around the cosmos, slipping past matter as though it didn't exist. For a long time, scientists believed that neutrinos couldn't be the answer to this enigma because they had no mass. But according to recent research, neutrinos can fluctuate between various flavors, and some variations of these particles may subtly favor matter over antimatter. Neutrinos may be the real cause of the imbalance that prevented the universe from annihilating if this theory is verified. The ability of labs to produce and preserve antimatter may be the most remarkable discovery. Since antimatter is destroyed when it comes into touch with any kind of matter, this was previously thought to be impossible. Small amounts of antimatter have, however, been successfully isolated for prolonged periods of time through tests at CERN and other labs worldwide, enabling in-depth analyses of its behavior. Scientists may be able to explain why symmetry was broken at the beginning of the cosmos if they discover basic distinctions between matter and antimatter. However, these findings also bring up more profound issues. What if the universe contains unseen forces that we haven't yet discovered? What if that imbalance is caused by unidentified particles? It is becoming more and more likely that our existing theories are not complete. A fresh scientific revolution comparable to the discovery of relativity or quantum mechanics may be possible if the physics we currently understand is merely the surface of a system of far deeper and undiscovered rules. We are getting closer to solving one of the biggest mysteries of the universe with every new experiment. However, at the same time, new questions come up that lead us to believe that the universe might be much more complicated and bizarre than we previously thought. Are we really approaching the final solution? Or will we uncover a bigger mystery than we anticipated from our search? Andrei Sakharov is one of the most innovative of the major names in theoretical physics. Sakharov, who is more famous for his contributions to the creation of the Soviet hydrogen bomb, took an unexpected career flip and went from military engineering to becoming one of the most influential theorists of the universe. It was he who came up with a theory that might explain why matter was preferred over antimatter in the universe. By suggesting that the fundamental principles of the world are not completely symmetrical, and that this minor flaw may have been the deciding factor that permitted human creation, his theories opened the door for a new understanding of physics. Sakharov developed three essential requirements in the late 1960s that must be fulfilled for matter to triumph over antimatter at the universe's inception. These requirements were later dubbed the Sakharov criteria, and they still serve as the cornerstone of any hypothesis that aims to explain the cosmic imbalance. The first need is that a process must produce more baryons than antibaryons, which are particles like protons and neutrons. This implies that, in some unidentified way, nature must be biased toward creating more matter than antimatter. The violation of C and CP symmetry is the second requirement. This simply implies that matter and antimatter must be treated somewhat differently by the universe. Every particle of matter would have an identical antiparticle if symmetry were absolute, and the universe would have been annihilated at the time of creation. However, current research indicates that some subatomic particles, like as K and B mesons, do, in fact, slightly defy that symmetry. At the beginning of the universe, this might have been sufficient to tip the balances in favor of matter. This imbalance must have arisen out of thermal equilibrium in order to meet the third requirement. This implies that some of those asymmetries had to freeze into the fabric of reality at the precise moment when the cosmos started to cool and expand quickly. All asymmetry would have vanished if the particles had had enough time to interact and achieve perfect equilibrium. However, this mechanism might have been necessary to guarantee the supremacy of matter over antimatter, because the early cosmos was a complete chaos with extremely high temperatures and densities. Although groundbreaking, Sakharov's theory is still lacking some key components. Although scientists are aware that these three circumstances had to exist, they are still unsure of how. As of yet, no experiment has been able to provide a convincing mechanism for this cosmic imbalance. New study, however, suggests that this process might have been significantly influenced by exotic particles or unidentified forces. The basic principles of physics may be significantly more intricate than we previously thought, if that is the case. Sakharov became a symbol of intellectual freedom and political resistance, in addition to helping to build contemporary physics. He defended scientific freedom and human rights against the Soviet regime, and was exiled as a result of his beliefs. He was a visionary who opposed physics and the repressive structures that constrained human understanding, and his legacy goes beyond science. Generations of scientists are still motivated by his theories today to discover the truth about the universe's beginnings. Although Sakharov's theory provides a rational framework for comprehending the disparity between matter and antimatter, there is a catch. No one has been able to pinpoint the precise way in which these conditions were used in the early cosmos. We are still far from a conclusive solution, but every new experiment gives scientists tiny hints that nature may have favored matter. What's lacking? What are we missing? Some subatomic particles, including B and K mesons, have already been shown to violate the CP symmetry. When these particles decay, their behavior deviates slightly from what is expected, suggesting that matter may really prefer antimatter in nature. However, that effect is so tiny that it is insufficient to account for the vast imbalance that exists in the cosmos today. To put it another way, there has to be more, some secret element that magnified that effect to cosmic proportions. Neutrinos are one of the major wagers made by science. These mysterious particles can travel across entire planets, stars, and even entire galaxies, like ghosts, and hardly interact with matter. According to certain investigations, neutrinos may break symmetry even more profoundly than mesons. If this is accurate, it may hold the secret to understanding how the early cosmos produced more matter than antimatter. the universe's own expansion is a major enigma as well. In addition to being an energy explosion, the Big Bang was a time of complete chaos during which enormous forces were at work. The interaction between matter and antimatter in the early universe may have been affected if the universe expanded asymmetrically. We still don't know how, but it's possible that the basic structure of space-time was molded to favor matter. However, the most extreme theory raises the possibility that there are undiscovered forces in nature. The strong nuclear force, the weak nuclear force, gravity, and electromagnetism are the four fundamental forces that we currently understand. However, what if the universe's origin was influenced by a fifth, secret force? The creation of matter may have been slightly skewed in favor of matter by particles known as dark bosons, according to some physicists. The confirmation of this idea would fundamentally alter our comprehension of the principles of physics. New questions come up every time we believe we have a solution. In the first trillionths of a second following the Big Bang, what actually occurred? Is a new physics model on the horizon? The only thing we know for sure is that the answer to this riddle will not only help us comprehend the past of the universe, but it may also fundamentally alter our future. If you were to look at the cosmos at its most basic level, you would find that everything is made up of a crazy dance of subatomic particles that appear and disappear in minuscule amounts of time. The principles of quantum mechanics control that invisible universe where nothing is constant and what we refer to as reality is merely a game of probability. However, certain of those particles have an enigmatic behavior that may hold the secret to the universe's preference for matter over antimatter. K and B Meson experiments have demonstrated that these particles, which have a short lifetime of trillionths of a second, decay slightly differently than their antiparticles. This phenomena, referred to as CP violation, implies that matter and antimatter are not treated equally by nature. Although this difference is a significant hint, it is too slight to account for the enormous imbalance that resulted in the creation of the universe as we know it. Apart from mesons, neutrinos are becoming a more fascinating component of this conundrum. Even though they hardly ever come into contact with substance, these particles can travel across entire planets without coming to a stop. They also have a special quality. As they move through space, they alternate between various flavors. This contradicts our perception regarding the stability of fundamental particles, since a neutrino can be born as one type and change into another type seconds later. However, what if neutrinos fluctuate between matter and antimatter in addition to between other types? According to certain investigations, neutrinos may be slightly biased toward matter, which could account for the universe's breaking of its initial symmetry. It would demonstrate that subatomic particles have an innate propensity to produce more matter than antimatter, which, if verified, would rank among the biggest discoveries in contemporary physics. The intrigue doesn't stop there, though. According to physicists, there may be a hidden family of neutrinos known as sterile neutrinos that interact with the universe in ways that are now undetectable. These particles may have influenced the formation of matter following the Big Bang, if they are indeed there. This could lead to the discovery of a new, uncharted area of physics, if our hypothesis is right. There are many mysteries in the dance of subatomic particles, and each solution we discover raises new ones. Is a new force of nature that controls the equilibrium between matter and antimatter about to be discovered? Or is there something more profound woven throughout the universe? It is essential to verify those theories in the real world if we wish to comprehend what transpired in the early cosmos. Theorizing is insufficient. However, how can we replicate the conditions of the Big Bang, which took place 13.8 billion years ago and featured energy and temperatures that are unthinkable? The solution is found in particle accelerators, which are enormous devices that collide atoms at nearly the speed of light, briefly recreating the universe's original condition. The Large Hadron Collider, LHC, situated at CERN in Switzerland, is the biggest and most potent of these accelerators. This device, which has a 27-kilometer circular tube, can accelerate protons to incredible speeds and collide them at precise locations to create subatomic explosions that resemble the events immediately following the Big Bang. In order to find proof of the symmetry violation that favored matter over antimatter, scientists examined the debris left over from these encounters. The aforementioned B mesons, which exhibit minor violations in the anticipated symmetry, are among the most fascinating findings from the LHC. This demonstrates that matter and antimatter are not treated in the same way by nature at the subatomic level. However, once more, that disparity is still insufficient to fully account for the events of the universe's creation. The baryon-antibaryon symmetry experiment, BASE, located at CERN as well, is another intriguing experiment that aims to thoroughly examine the characteristics of antimatter. In order to understand why antimatter vanished and matter persisted, scientists attempt to determine whether, for some reason, it behaves somewhat differently from matter. The discovery of even the slightest variation in the mass, charge, or lifetime of antimatter particles may point to the existence of a secret force that influenced the development of the universe as we know it. However, research is not limited to Switzerland. One of the most ambitious experiments in this sector, T2K, Tokai to Kamioka, is located in Japan and examines neutrino behavior. According to preliminary findings, neutrinos may in fact break the symmetry between matter and antimatter, supporting the theory that they were a major contributor to the cosmic imbalance. If verified, it might be the first hard proof of one of the processes that made the cosmos possible. We still lack a conclusive explanation in spite of all these developments. Although there are still many unanswered questions, we are getting closer to understanding what tilted the cosmic balances in favor of matter. We learned that the universe might be much stranger and more complicated than we first thought with every new experiment. And what if particle physics isn't the only explanation for this mystery? What happens if we are ignorant of something much more basic? The laws of the cosmos, as we currently understand them, may need to be revised as we approach a new era of science. Unquestionably, one of the most ambitious scientific projects ever built by humans is the Large Hadron Collider, LHC. This massive particle accelerator, which is situated at CERN, on the French-Swiss border, is dedicated solely to revealing the universe's darkest secrets. For fractions of a second, it recreates the conditions of the early cosmos by accelerating protons to near light speeds and colliding them at unthinkable energy through a 27-kilometer circular tunnel. What precisely are scientists searching for, though? The LHC's primary goal is to determine why matter, not antimatter, survived. Unstable particles called B mesons, which have been the subject of years of research at the LHC, provide one of the best hints for this solution. These particles have been found by physicists to slightly favor matter by faintly violating CP symmetry. However, the vast disparity we witness in the universe cannot be explained by the observations made thus far. This implies that forces or unidentified particles that were essential to the creation of the universe must still be there. Dark energy and dark matter, which make up around 95% of the cosmos yet are still mysteries to science, are another mystery that the LHC is attempting to solve. According to certain ideas, the imbalance between matter and antimatter in the early stages of the Big Bang might have been impacted by dark matter. The discovery of dark matter particles at the LHC could fundamentally alter our knowledge of how the universe came into being. Furthermore, the discovery of new fundamental forces of nature is one of physicists' biggest hopes. The strong nuclear force, the weak nuclear force, gravity, and electromagnetism are the four forces that we currently understand. But according to some evidence, there may have been a fifth, unidentified factor at work at the beginning of the universe that gave matter a minor advantage over antimatter. If such a force is real, it might hold the secret to solving one of the biggest mysteries in contemporary science. However, what if the LHC showed that our existing theories are incorrect rather than merely finding new particles? What if our understanding of physics is but one aspect of a much bigger picture? These problems are not just conjecture. When new information contradicts our preconceived notions, they are becoming closer to becoming reality. There is still plenty to be discovered at the LHC. Every experiment moves us one step closer to the truth, and every particle collision produces trillions of data points that need to be examined. However, the LHC might not have the answer to this problem. One of the most enigmatic particles in the cosmos, the neutrino, may hold the key. The neutrino is one of the few particles that defies every known law of physics. It is extremely elusive, tiny, and almost massless. It travels across entire planets without coming into contact with anything. Unbeknownst to you, billions of neutrinos flow through your body every second. Nevertheless, despite their spectral characteristics, neutrinos may have the solution to one of the universe's biggest riddles, the disappearance of antimatter. Neutrinos have fascinated scientists ever since they were discovered. At first, it was believed that they had no mass, but studies revealed that they do have a very small mass, not zero. Given that it suggested that neutrinos might act much more weirdly than previously thought, this was one of the most groundbreaking discoveries in particle physics. The ability of neutrinos to fluctuate between distinct types as they move through space is one of their most enigmatic properties. This implies that a neutrino can have one kind at birth and change into another throughout time. This characteristic is exclusive to subatomic particles and raises the possibility that neutrinos were a major contributor to the imbalance between matter and antimatter. Neutrinos may fluctuate somewhat differently from their antimatter counterparts, the antineutrinos, according to experiments like T2K in Japan and NOVA in the US. This is an astounding discovery. If this violation is verified, it may indicate that the real forces responsible for shifting the cosmic balance in favor of matter were neutrinos. This would definitively explain our purpose for being here. However, there is a deeper significance to this notion. The universe might be full of unidentified particles that follow laws we haven't even thought of if neutrinos truly break the symmetry between matter and antimatter. According to some physicists, there may be a unique kind of neutrino known as the sterile neutrino that doesn't interact with any of the recognized natural forces. The existence of these neutrinos may hold the secret to understanding the early history of the universe. An even more audacious hypothesis is that neutrinos might actually be their own antimatter. According to this theory, which is called the Majorana mechanism, neutrinos may have created a cosmos where matter persisted and antimatter vanished. Verification of this theory might transform our knowledge of the fundamental structure of space-time and answer one of the biggest enigmas in physics. Neutrinos are getting more and more interesting with every new experiment. In addition to helping us forecast the direction of physics, they might hold the secret to the universe's past. We would be dealing with a finding as significant as Einstein's theory of relativity if we could establish without a reasonable doubt that neutrinos break the symmetry between matter and antimatter. And what if the fabric of reality conceals something even more profound? What if there are other forces and particles besides neutrinos that we can't even imagine? The hunt for the solution is far from over. Finding out if the cosmos is biased toward matter and what it means for science's future is the next step. If there is one thing that contemporary science is sure about, it is that the cosmos is governed by incredibly exact laws. Everything appears to follow a set of unchangeable laws, from the motion of galaxies to the structure of atoms. The asymmetry between matter and antimatter, however, is the one thing that defies that reasoning. In addition to allowing the universe to exist, this imbalance raises the possibility that the universe secretly favors matter. However, is that tendency a cosmic aberration or a basic feature of the universe? Scientists examine the interactions of fundamental particles in carefully monitored labs to find the answer to this issue. The equations and experiments should represent the universe's true preference for matter. But according to every physics law currently in existence, matter and antimatter ought to have been formed in exactly the same quantities. An unseen component of this puzzle is missing. The initial moments following the Big Bang could be the source of this bias. According to some scientists, the cosmos underwent a phase change, during which time specific particles might have interacted with forces that we haven't yet discovered. If this is accurate, it may indicate that space-time has inherent characteristics that have always favored matter. On cosmic sizes, the cosmos may not be quite symmetrical, according to another theory. Small changes in matter density can be seen if we look at large-scale structures, like the distribution of galaxies. Could these changes be signs that matter always had a tiny advantage over antimatter from the beginning? Or are they just random fluctuations? And what if something even more fundamental is the cause of the bias in favor of matter? According to some theorists, this imbalance may have been caused by previously unidentified particle kinds. The so-called dark bosons, which could interact with matter in a subtle but significant enough way to guarantee its domination in the cosmos, are among these theoretical options. Our current understanding of physics would be lacking if we were to actually find that the cosmos is biased toward matter. Maybe the universe is governed by unspoken rules that determine which particles endure and which disappear. If so, the next important issue is, what is the driving force behind this process? Dark energy, one of the universe's greatest mysteries, is directly addressed by this research. Does the asymmetry between matter and antimatter have anything to do with this unseen force? Maybe we're looking at the issue from the incorrect angle. The expansion of the universe is the only thing that scientists are certain about. Few, however, anticipated that this expansion would pick up speed. Galaxies are being pushed apart at ever-increasing rates by an enigmatic, imperceptible force that no one can identify. One of the biggest mysteries of contemporary physics is the origin of this force, which has been termed dark energy. However, what if that energy was the key to comprehending why matter prevailed over antimatter? Approximately 68% of the cosmos is made up of dark energy, although its precise nature has not yet been determined. The idea that it is a basic characteristic of space-time itself, something that has always existed and subtly but significantly affects the structure of the universe, is one of the most widely accepted theories. If this is accurate, Space-time may not be neutral at the beginning of the universe, but rather have properties that favored matter. Dark energy may be related to a fifth fundamental force of nature, according to an interesting theory. The strong nuclear force, the weak nuclear force, gravity, and electromagnetism are the four fundamental forces that we currently understand. Some studies, however, suggest that there may be an unidentified interaction, a sort of invisible field that exerts uneven effect on matter. If the force is real, it might have been the cause of the early universe's disruption of the symmetry between matter and antimatter. However, an even more unexpected scenario exists. What if the lost antimatter had a side effect of dark energy? According to some physicists, the destruction of antimatter might have created a kind of echo in space-time, creating the repulsive effect that we now see as the universe's accelerating expansion. If this theory is correct, dark energy is a remnant of the cosmic conflict between matter and antimatter, a scar from the past. Through astronomical observations and experiments, scientists are attempting to discover the answers. The European Space Agency, ESA, recently launched the Euclid Space Telescope, which was intended to map the cosmic distribution of dark energy and matter. Its findings might show trends that suggest whether dark energy is related to the universe's initial asymmetry in any way. However, what if dark energy isn't the solution we're looking for? What if there is something more profound that is beyond of our grasp? A thorough reassessment of the basic laws of physics may be the next stage in scientific inquiry, rather than merely looking for invisible particles and forces. Could a scientific revolution be imminent? Is it possible that our quest to comprehend the universe's beginnings may ultimately lead us to realize that we need to completely rewrite our conception of reality? There are additional questions with every new finding. One thing is for sure, though. We are getting closer to comprehending what actually occurred in the early universe. And as we learn more about this research, an intriguing new question comes to light. What if antimatter was more prevalent in other universes? Science has long believed that our cosmos is special. Everything we know was thought to have originated from a single event known as the Big Bang. But in the last few decades, this viewpoint has started to be challenged. Many physicists today think that our universe might be one of an endless number of universes, each with its own set of physical laws. If this is accurate, an intriguing hypothesis emerges. What if antimatter prevailed over matter in some universes? The Big Bang might not have been the only cosmic event of its sort, according to the multiverse idea. Rather, it could have been one of several births of universes, each with slightly different properties. With a little bias toward matter, some of those universes might have formed planets and galaxies by adhering to the same laws as our own. In others, however, antimatter might have prevailed. The structure of a universe dominated by antimatter wouldn't alter significantly from our own. With stars, planets, and even life forms made of positrons, antiprotons, and antineutrons, the rules of physics would operate in a similar way. Everything would appear normal to an observer in that universe until they came into contact with regular stuff, which would cause a catastrophic energy explosion. However, how can we put this theory to the test? Is it possible to identify whether parallel universes exist? Strange cosmic abnormalities, including specific patterns in the cosmic microwave background radiation, may provide the evidence, according to some scientists. Little variations in the distribution of this radiation, which is similar to the fingerprint of the Big Bang, could suggest that our world formerly interacted with other universes. The multiverse may be proven to exist if there are indications that some regions of our universe were impacted by something external. In addition, some interpretations of string theory, one of the contenders for a single, cohesive theory of physics, propose that our reality might simply be a membrane in a multidimensional space where other realities coexist with ours but are hidden from view. If this is accurate, it may indicate that antimatter-dominated universes are isolated not just geographically, but also inside the fabric of reality itself. Our knowledge of the world would be completely transformed if we could one day prove that there are universes where antimatter prevailed. However, this would raise a more profound question. If there are alternate realities, what other rules of physics might be different? We would only be beginning to realize how enormous life really is. The standard model of particle physics has been used by scientists for decades to explain how the universe functions at its most basic level. Every experiment to date has verified this theory's predictions with astonishing accuracy, and it describes the forces and particles that govern reality. But there is a growing and unsettling issue. When we attempt to explain the asymmetry between matter and antimatter, the mathematics just does not add up. This raises the audacious question: what if the standard model is flawed or even incorrect? The main issue is that, in spite of its accuracy, the standard model does not adequately explain why matter has triumphed over antimatter. Although particles like K and B mesons are known to break CP symmetry at extremely small levels, the vast imbalance seen in the universe cannot be explained by these variations. Stated differently, the figures just don't add up. This has made researchers wonder if there is a new physics out there that we haven't yet discovered, something that goes beyond the standard model. According to certain hypotheses, the fate of the universe in the early minutes following the Big Bang may have been impacted by unidentified particles, possibly a new kind of boson or even a hidden basic force. However, no experiment has been able to find these fictitious particles to date. The standard model's inability to adequately account for gravity is another significant issue. Gravity is described by Einstein's theory of relativity on cosmic scales, but the equations lose their meaning and become unstable when applied to the quantum realm. This implies that there is a serious flaw or gap in our comprehension of reality. But how can we determine the right response if the standard model isn't complete? One idea is that we require a theory of everything, a mathematical model that explains gravity and all other fundamental forces in the universe. This issue is attempted to be resolved by theories like loop quantum gravity and string theory, but none of these have been verified empirically to date. It's possible that particle accelerators themselves contain some hints about this new physics. At the Large Hadron Collider, LHC, experiments are looking for indications of particles that do not fit the standard model, like possible extra Higgs bosons or even evidence of new spatial dimensions. The greatest revolution in physics since Einstein may be imminent if any of these predictions come to pass. However, there is an even more radical possibility. What if we are misinterpreting the data? What if our conception of the universe's basic laws differs from reality? On a deeper level, matter and antimatter might only be expressions of something even more fundamental and mysterious, according to some theorists, who contend that the idea of particles themselves is merely an approximation of reality. In actuality, we shall be confronted with a conundrum that tests the limits of contemporary physics until we can reconcile this mathematical disparity. There are only two possibilities if matter defeated antimatter, yet our equations show that this shouldn't have happened. Either we haven't found something important yet, or our ideas are flawed and need to be redone. Is science about to enter a new era? In the upcoming decades, will this riddle be solved at last? Or does the cosmos still contain mysteries that will test our knowledge for many years to come? We are still searching for the truth, and we might find more than we could have ever dreamed. One of the most unusual and hazardous materials in the universe is antimatter. According to Einstein's well-known equation, E equals mc squared, when a matter particle collides with its antimatter counterpart, the two annihilate one another in a blast of pure energy. The enormous quantity of energy released by this process, called annihilation, makes antimatter one of the most effective energy sources that science has discovered. However, what if we could eventually create and store a lot of antimatter? How might humanity be affected by that? Only very small amounts of antimatter are now created in labs like CERN. Due to the need for highly sophisticated particle accelerators and a containment system that keeps any matter from coming into touch with them, producing a single gram of antimatter would take thousands of years and cost trillions of dollars. Only a few atoms of antihydrogen, kept for a fraction of a second before annihilating, have been the largest amount created thus far. A more effective approach to produce and store antimatter may transform humanity in a number of ways if it were discovered in the future. The production of energy would be the first and most noticeable effect. 1 kilogram of antimatter might provide as much energy as a hydrogen bomb due to the incredibly efficient annihilation between matter and antimatter. This implies that, in theory, we could construct power plants based on antimatter that could generate electricity without the radioactive waste that comes with traditional nuclear reactors. Space exploration is another possible application for antimatter. Our spacecraft now run on chemical fuels, which are inefficient and heavy. Antimatter-powered spacecraft might travel at amazing speeds, significantly cutting down on the amount of time needed for interplanetary or even intergalactic travel. It would take weeks or even days to go to Mars, compared to months today. However, there is a huge issue. Antimatter is the most hazardous material that is currently known. Any malfunction could cause unthinkable explosions if it is not stored correctly. An whole city might be destroyed by the energy contained in 1 gram of antimatter. The military's employment of this technology is seriously called into doubt by this. Nuclear bombs, which might signal the end of warfare as we know them, or the start of an era of unimaginable terror, would be significantly less potent than antimatter weapons. We could also be able to better grasp why matter prevailed in the cosmic struggle in the early cosmos if we could produce significant amounts of antimatter. The grand mystery of why we exist might finally be answered by examining the characteristics of antimatter in a controlled setting, which may show minute distinctions between matter and antimatter that we have not yet noticed. Our current technological capabilities are far from sufficient to produce antimatter on a large basis. However, science is developing quickly, so in the upcoming decades or centuries, what seems impossible now might become achievable. Will we be ready for such tremendous power? Or will we be tinkering with uncontrollable forces? The pursuit of more effective energy sources is, if anything, what propels human progress. We have always looked for ways to get more energy from fewer resources, whether it is nuclear or coal. However, the energy potential of antimatter surpasses all of these technologies. No other energy source can release all of the energy contained in the particle's mass in a single annihilation reaction between matter and antimatter. However, will antimatter ever be a practical source of energy? The concept is not new. Antimatter reactors, which may supply limitless energy for cities, automobiles, and spacecraft, have been the subject of decades of conjecture by scientists and science fiction authors. But there is a basic issue. The visible cosmos does not naturally contain substantial amounts of antimatter. It must be produced artificially, and doing so comes at an enormous cost. The expenses are prohibitive at CERN, where antimatter has previously been created and stored. The production of a single milligram of antimatter would cost billions of dollars. This is due to the fact that the process necessitates massive particle accelerators, intense cooling, and highly developed magnetic fields in order to confine the antiparticles and prevent them from coming into contact with ordinary matter and annihilating right away. Everything would be different if we could create antimatter in a more economical and effective way. The uses would be groundbreaking, small, incredibly powerful energy sources. With a negligible amount of fuel, an antimatter reactor might provide energy for a whole metropolis. Extremely fast spacecraft. Antimatter-powered spacecraft could reach speeds near that of light by directly turning mass into energy, opening the possibility of interstellar travel. Space exploration would be transformed. Since we wouldn't have to transfer massive amounts of fuel, colonizing Mars and other planets would become much more practical. The technical difficulties and risks associated with antimatter reactors must be taken into account before becoming overly enthusiastic about the concept. Antimatter storage is a major issue in addition to its exorbitant cost. Catastrophic explosions might occur from any containment system failure, releasing more energy than any nuclear bomb ever made. Production presents another difficulty. Even the most sophisticated technologies on the planet today can only generate a small number of antimatter particles at once. Tons of antimatter would be required to power a spacecraft or an energy reactor, which is well beyond our current capacity. An even more exciting prospect, though, is that antimatter may be collected naturally. According to some scientists, there may be a lot of antimatter in the universe's most active areas, like pulsars and black holes. We might be able to avoid the issue of artificial production if we could create the device to gather it straight from space. The hunt for antimatter-based energy sources is still ongoing in spite of all these obstacles. We shall be confronted with the biggest energy revolution in human history if we are able to get past these obstacles one day. We still have a lot to learn about the forces governing the universe, though, before we get there. One issue still stands as we look for solutions. Will what we find alter all we think we know? Or are we really getting near to unraveling the enigma of existence? There is still much to learn about the universe's origins. The solution remains elusive despite decades of tests, ever more powerful particle accelerators, and groundbreaking hypotheses. We are not, however, in the dark as a result. Conversely, each new finding advances our understanding of reality. And as we go into the 21st century, we may be close to finally solving this cosmic riddle once and for all. Neutrino experiments, like DUNE in the US and T2K in Japan, are offering more proof that these particles might have broken the symmetry between matter and antimatter at the beginning of the universe. One of the biggest breakthroughs in contemporary physics would be the confirmation that neutrinos caused that imbalance. However, the question of why neutrinos act in that manner still stands even if that discovery is verified. We might discover forces and particles we never thought about as a result, opening up new levels of wonder. The Large Hadron Collider, LHC, and its successors will continue to investigate the rules of physics at ever smaller sizes in addition to neutrinos. It is hoped that future investigations will uncover evidence of new dimensions of space-time, or perhaps exotic particles like the fictitious dark bosons. The confirmation of any of these theories could fundamentally alter our conception of the universe's beginnings. The investigation of dark energy is another development that may provide answers. Studying this enigmatic force could reveal information about what transpired in the first trillionths of a second following the Big Bang, if it was indeed involved in the separation of matter and antimatter. In addition to aiding in the mapping of dark energy dispersion, the recently launched Euclid Space Telescope may provide surprising findings in the years to come. Few scientists, meanwhile, are willing to entertain the notion that we might never discover a conclusive solution. What if there is no obvious reason why matter predominates in the cosmos, and it is just as it is? This would imply that there is a limit to our knowledge of physics, and that some problems may never be addressed. However, science's history shows us that people always manage to overcome the most daunting obstacles. In the past, we believed that we would never glimpse a black hole, learn the age of the universe, or comprehend the makeup of stars. But we've accomplished all of that and more. If there's one thing science teaches us, it's that the more we learn, the less we know. Will we ever be able to unravel this mystery? Nobody knows for sure. However, one thing is for sure. The quest for knowledge will never end as long as there are questions. And when the solution is eventually discovered, it might take us to a level of comprehension of the cosmos that is unthinkable to us now. The last and most important question is also the most challenging to answer. Will we ever be able to know for sure why the universe exists? Numerous answers that previously appeared impossible have already been given to us by science. We have found gravitational waves, uncovered the structure of the atom, described how stars function, and even taken the first picture of a black hole. Before they occurred, each of these accomplishments appeared unattainable. But perhaps the biggest problem we have ever encountered is the asymmetry between matter and antimatter. Some people think the solution is close. We may get the answer within a few decades, thanks to developments in particle accelerators, cosmology, and neutrino research. The answer will be obvious and conclusive if we can show that the violation of primordial symmetry was caused by a new particle or force. However, it is also possible that this question will never be fully answered. Maybe the rules that govern the cosmos are more complex than we can comprehend. Beyond general relativity and quantum mechanics, we may require an even more sophisticated theory. This would usher in a new era of physics, one in which understanding the universe's genesis would need the development of whole new ideas. The question of whether we truly want to know the answer is another fascinating one. Some people who were hoping for a more profound explanation could be disappointed if we find that the universe's existence was due to quantum chance. However, our understanding of reality might be drastically altered if we discover that matter was favored by a purpose or underlying structure. Whatever the solution, humanity is motivated by the quest for this understanding. Why? Is the core of who we are. Our curiosity is limitless, regardless of whether we are venturing into the ocean's depths or the boundaries of intergalactic space. How far we are willing to go to get the answer may be more important than whether we will ever know it. The universe always shocks us if there is one lesson to be learned from it. And perhaps its greatest secret will come to light when we are really ready.